3, 2, 1, let's go. So welcome back after the coffee break. Now we are going to have a session regarding practical examples and future direction of data, AI and EOSC. How this is going to be organized. So basically, step by step, I will invite the speakers on the stage. They will give the presentation. We are going to have a possibility to ask 1 or 2 questions regarding the time, and then the speakers are going to sit down on the chairs here. And in the end of the session, we will have approximately 20-25 minute moderated discussion. And please, I incentivize all of you to ask questions, and to do it as vivid as possible. So with this, I would like to invite the first speaker, Mr. Jan Kočí from Technical University of Liberec. That he is a digitalization and AI expert. He focuses on applying machine learning to industrial processes, industrial laser automation, and advanced technologies for space. So basically, to the South Moravia from north of Bohemia, welcome here on the stage and give him warm welcome. Thank you very much. Yeah.
So, good morning, everyone. I'm Jan Kočí. I'm from Technical University of Liberec, from Institute of Nanomaterials, Advanced Technologies and Innovations. Long name, and that's because we are doing a lot of things. Because of tough timing, I would like to be short and don't want to bother with some more details. But at the very beginning, I would like to say, because of AI, so I would like to prepare the presentation with AI, with generative AI. Such a stupid idea, because I spend more time for prompting AI in order to create proper slides, in order to say what I want to say, to generate the images I want to see. So I would like to have it, I think, faster doing it myself. So next time I won't do such a mistake. Well, so our institute is organized in 3 research directions. One is nanomaterials in the natural sciences, biology, chemistry, and creating new materials and doing something which I do not understand, because I'm originally IT developer, IT guy, and working almost 35 years for digitization and implementing digital solutions in industry. But anyway, they are famous because of the nanomaterials and that stuff. The second one is competitive engineering. Those guys are more understandable for me, because those are mechanical engineers. They have also the department for checking engines and transmissions. And there are also department which is creating composite materials, which is also something which is important in nowadays. And there are big department which is using additive manufacturing, which is also something which is material related, because for additive manufacturing and 3D printing, material is the key component. And system integration is the third research direction I'm leading, and this is something we want to do, I think, Industry 4.0 related topics. So everything what belongs to Industry 4.0, sensors, taking data, working with the data, analyzing the data, and creating also some fancy UI for users. My apologize is that I'm IT guy, I'm not the material expert. So if you want to ask me for materials, for some particular details about material research, do it, of course, but might be I will forward that to my colleagues afterwards. Anyway, digitization and automation is something which helps us, and because in industry it's, I think, quite familiar, but in research it's something which can help us also, because now we are able to use such technologies in order to make our research efficient, might be to make our research faster, and to provide brand new stuff which is not able to do it with a regular, might be physical experiments. So AI transformation makes us also to help with or to work with the data and to move to, I would say, data-driven methodology. And something helps us, because the previous presentation talked about data, datasets, training and using the data. Of course, this is essential. But as soon as we have some data, as soon as we have some models, as soon as we have some tools to use it, and as soon as we have also experienced people who can use it, we can say, okay, so this is the time for predicting stuff. So we can use the data and predict something in order to make it faster or more better. And our department especially focuses to make the digitization in our institute. So we say, okay, so this is from lab to algorithms. This is the change. So we can, in material design particularly, we might predict some material properties, for example, some physical or mechanical properties, in order to find out the proper material composition, find out the proper material creation in order to obtain it properly. So that's something which obviously can be used. We can also, in material design, we can also use it for structure discovery. I mean some structures or crystal structures or molecular structures. So I've been on some fancy AI conference where they also create the complete molecular structure via using LLM. So that's, I think, something we can obviously use, and we are using it in our institute in material department. And as soon as we have such data and simulation stuff ready, of course, we are using some simulation for simulation on some proper situations, for example, how it will behave in such specific situation. Can you switch the slide, please, or someone? Yeah. Okay. So, and because of my experience with the generative AI, which is almost based on LLMs or in multimodal LLMs, so LLMs can help us, obviously, yes. And I think a lot of us is using LLMs, either ChatGPT or whatever else, for at least for summarizing, for example, or once we are creating proposals. So sometimes it's much better to help ChatGPT than write it in our own. On the other hand, we need to review it afterwards. But it's also helpful when we want to make some hypothesis creation, because it's also be able to generalize it, to use a lot of data, and creating also some literature research. So something is of course helpful, but must be used, I think, in a good manner. Of course, LLMs and experimental design or continuous learning, because we can make it in a standard loops. So in our institute and our department helps our researchers to use at least standard large language models, but we also implement some specific solution made on open source LLMs in order to train it on the particular data, because we are Institute of Applied Research, so we have also some industrial partners. So they like to have something. They say, hey guys, we have a lot of documentation and we need to search very rapidly all of the documentation, and we want to grab the particular information. So it cannot be on a ChatGPT because it's the internal documentation. So we provide them some LLM solution trained on Olama's open source model, but we use it also in our institute for our researchers. So we put there all the research documentation in there, and we also preparing some fancy platform within EOSC and national repository. So this will be the part of our intention also to help to have the information complete. So of course, digitization at all can save the money because of making it more efficient and make it faster. But what is key, I think, is also to make the reproducibility, for example, because it's something which, as soon as you have it automated, you can be sure that the process is always the same, that the data taken are reliable. So you can do it again the same way. And that's something which we are also working in our institute. Also, it's not as easy as it can look like, because you're working with the researchers in a different split of age. So young people might be, they are fun for tablets and just scanning, but might be some experienced people, more experienced people, they would say, okay, fine, I like digitization, but my pen and my note, which is paper, is much faster and it's much more simple to work with it. Get rid of all your digitization stuff, and we don't like it. Well, but that's something we need to explain them, that sheet of paper is not as easy to reuse afterwards. So take the metadata from there. Take the proper data. So take the reliable data. Have it data at proper time from that sheet of paper, which is anyway lost in a laboratory. So that's something we need to be in charge of. So we need to say, okay, what do you need in order to be familiar with the digital solution and have it as easy as it would write the note on the sheet of paper. That's something which helps us to make the digitization in real life. And on the other hand, it means that without this, we don't need to have, or we cannot have AI or anything data-driven, because I cannot train a model on a sheet of paper. Of course, I can, because I can use the multimodal LLM to scan the sheet of paper and use it, but it has no sense. Of course, digitization and all the stuff we are using helps us to be more fair, because as soon as we have digital solution which is used in a lab, I mean, we have also proper laboratory tools. So we can create automated documentation, we can create the proper metadata, we can be sure that the proper metadata are in place, and we can also be directly connected to the repository. So this is our intention of creating to direct connector to our material repository in order to be sure that everything works without people. And this is something we can, or we are able to help our researchers to do the fair and open science policy, fill it, but not to be as tired by typing this, typing that, doing that stuff and that stuff. So this is something which we want to do and we are doing in our everyday job. But frankly speaking, this is tough work. But we must succeed, because we need to make even research more efficient and to be able to move forward, because that's the vision and that's the future. Well, this is the end. So I'm gonna save the time. That's fine, right? So if you have any question, I would like to answer it. In field of digitization, don't worry. But in field of materials, be careful.
Thank you very much for the presentation. So now we have a time for one, maybe two short questions. So from the audience, anything? From Slido? Oh, you? Okay. Yeah. Perfect.
Thank you. Thank you for the presentation. I was just curious whether in your field you are using some sort of, or if it is a standard to use some sort of a digital lab books or these kind of things.
Yes and no. We are going to use it, and we are also implementing some standard solution. We are in the material MATEC, which is material work group. So there are some tools, but we have our own tool which is customized for CXI or for TUL, which helps us to make it might be in a different way. But this is something obviously we are using. We call it DDR. But that's what I'm talking about, the sheet of paper. So we are just in a process of a change to make all of our researchers to use it, because otherwise it has no sense.
Okay. Other question? Anything on Slido? No question. Okay. Can you elaborate one more thing regarding your when I was introducing yourself, so I was mentioning space industry. So I know that the Technical University of Liberec is very well known for the nanomaterials, nanospider, etc. And how you are working with the space industry.
This is something we are working in intention of our National Center of Competence for Industrial 3D Printing. So we are going to prepare some coating for 3D prints which can be used in a space. Of course, I'm not the expert, so I only know that for example, for digitization, it's one piece of work, because we collect all the data, we use the data, and we optimize the process in order to be sure that everything is printed properly and coated, because it's some metal coating which must be put on the surface. So this is something we want to also implement into space, and we use some special nanomaterials which are put in place.
Okay. So thank you very much once again.
Thank you.
Thank you. And if I may ask you, please take the seat on the podium, and we will continue with the flash talks. So the next speaker, it's going to be from Masaryk University, Digital Pathology Using Artificial Intelligence in Practice by Tomáš Brázdil. And Tomáš is an expert in computer science and formal methods, where he focuses on system verification, algorithmic game theory, and automatization. And what I know about him, he was as well consulting with some financial sectors, you know. So maybe if you look on the topic of the presentation, maybe it could be interesting if there are any companies to invest in that sector, because this guy knows the finance as well. But as all the podcasts mentions, this is not an investment tip. This is just a comment of the moderator. So welcome on the stage.
Thank you for the introduction. I think that the description of my work is very, very old. For past 5 or 6 years, I am just in medical computer science and AI in medicine, like mostly the digital pathology. So I'm going to talk about, I'm going to talk about the work we do at Masaryk University, at Faculty of Computer Science, Faculty of Informatics, and Institute for Computer Science in the group called Rationai, and funded by Biomet AI twinning project. So first, let me say a few words about pathology. I think that hopefully most of you don't have a direct experience with it, but what is histopathology? So it's part of medicine where people are examining tissue samples. So in this case, the most common variant is examination of tiny slices of tissue under an optical microscope. So you have here a sample of prostate cancer, and the pathologist is simply looking at the glass and searching for the pathology. Now, as everything nowadays, this process also started to be digitized. So in digital variant, we have the same samples. So we have still, the doctors have to extract the tiny slices of tissue, put it under the glass, stain it with colors, and then everything is digitized. So there are some specialized scanning microscopes that produce large images of from the microscope, and they are stored somewhere and then analyzed either by pathologists themselves, or of course, when it's digitized, we can use AI. So we are trying to develop something which automatically analyzes the samples. And how does it work? So this is an example of our work, and also the pathologist is Rudolf Nenutil from MMCI. So this is really the stuff that we do. So here you can see the same image of prostate, sample from prostate. And the yellow stuff here is the prediction of our model, which tries to find prostate cancer. Okay, so this is the product, basically. This is what it does. And now the question is how such a system is trained on the data. I'm not going to describe here the process, because this meeting is more about data and projects and processes. So I will just say, okay, this is what we do. And of course, there are many more organs, many more problems, so many stainings, etc. So this is just a single example, but we of course work on much larger scale of problems. What I think is more interesting from the point of view of hopefully you as an audience is the process, how we work with the doctors, with the pathologists on creating such systems. And here, I think there is I've seen some misconception on AI, on machine learning in some groups. How does it work? Because I think that the standard view is that, okay, there are large data sets, we take them, we train some models on them, and then have the system. But at least in our case, it doesn't work this way. So it's, say, really tight and constant collaboration between the pathologists and computer scientists. So it starts with problem formulation, where the doctor has to formulate the medical problem, and then the computer scientist has to somehow say, okay, yes, this makes sense, we might be able to solve it. Then the pathologist selects the data, so in this case, the glasses, the samples, and even this typically is in collaboration with computer scientists who say, okay, this might be really something that we can process. Then it's scanned, and computer scientists have to look at it and say, okay, this is really good or bad. We cannot use such data, it's nasty. Then, of course, there is metadata problems, so like annotations and maybe clinical information about the patients, etc. This is really difficult thing to deal with, as we discussed just before this session with my colleagues. Typically, metadata is transferred using Excel sheets or something like that. So it's messy and very hard to preserve and work with. Okay, at the end, data are transferred to computer scientists. In our case, these are sets of very, very large images. So the microscopy, the image from the microscope is gigapixel image. So if we have a data set of, say, thousands of images, it's in terabytes. If it's very large, so nowadays some groups train foundation models for pathology. These are trained even on millions of whole site images. Then you are in petabytes and more. So it's very large. Then we train something, and then we immediately discuss the results with the pathologist. So there is this closed loop of iteration, doctors and pathologists, and we always need to communicate results, communicate data, etc. So this is the hardest part, and we have to do that. The data itself, as I said, so the main stuff that we work with are whole site images, so the big gigapixel images of tissue. And typically, if you have a patient, there are several images from single person. And of course, we also have other types of data. So if you want to know, for example, whether a person has a particular type of tumor, you have to look into textual medical report. And there are people also in our group that try to decode this information from unstructured text data, which is quite difficult. And of course, clinical, genomic, and so on. So lots of types of data that have to be put together in some sensible way in order to train a model. As I said, we are funded by a twinning project. Currently, it's the main source of funding, Biomed AI, where we use the infrastructure. We use sensitive cloud because we have sensitive data, so we are using a very specific environment that allows us to get sensitive data relatively easily, just use simple contracts on data processing. And then we use the technical infrastructure, of course, storage and GPUs and some systems that allow us to do the training. And of course, lots of the stuff is about quality of data, cleaning data, etc. As you can see in my picture here, it's even difficult to find AI there, right? AI is a really very tiny part of the work. Lots of the stuff is simply data processing. And of course, the application in hospital, where we have to run it, we have to show it to the doctors, the pathologists, in a way that they are used to, because otherwise they won't be able to evaluate the results. Unless it's in the way they are used to work, it doesn't work, okay? So these are the most crucial things. What model we use doesn't matter, basically. Okay, I will skip this. In our group, we have also developed a viewer for the images that's particularly well suited for our purposes, for the research and for specific annotations and for displaying complex outputs from the models. And we also have, say, experimental case browser and all this. This is a system for going through patients and looking at their data. And all this is deployed at MMCI in an experimental way. So we also have to transfer lots of data in real time, basically, in order to operate this and to test whether the AI not only works in statistical sense, but in practical sense, so that it can be used for diagnosing cases. This is just my last part, because I am fascinated by how some groups think. So if you ask pathologists about AI in digital pathology, so some of them say, okay, I don't want anything like that. I want my optic microscope, no digitization, no AI, nothing. I just want the old way, nothing new. There are some pathologists who say, okay, it looks interesting. At least I can try it. And then if you ask, what does it mean to solve something with AI? Okay, I have lots of work. If it doesn't bother me, and sometimes it helps, yes, this is a success. If you look into computer science literature on digital pathology and AI in digital pathology from, say, 2018, you will find papers where they claim that the problem is solved because the system already outperformed the human experts. Typically, it was quite a silly study where they took some random images and showed them to pathologists and to some trained models, and statistically they evaluated that the confused human was somehow unable to find the cancer. Okay, but if you read it, you say, okay, this is done. No more pathologists in the world. Not necessary. Okay, time flies, and if you look into papers in 2023, 24, and maybe 25, you will find something like this. Wide adoption is difficult, and there are many reasons. There is no standardization of formats of images from scanners. There is no standardization anywhere. Many pathologists and medical specialists in general simply refuse to use these solutions. Every hospital has its own information system, so it's very difficult to integrate with the AI-based systems. If you have your prototype, you have to persuade the bosses of the hospital that they will allow you to use that, and then they have to buy it, and you have to sell it. And many companies simply found out that this is the hardest part. So somebody has to pay for it. This is the point where most research. And okay, so that's it. As I said, I was talking about the research and development of Rešnaj group at Masaryk University. It's maybe still a relatively small group, but it's already more than 30 members. We are also collaborating with ICS at Masaryk University, where there is a team controlling the infrastructure. And within the Biomet AI project, we collaborate with Medunik Graz, where there is a huge biobank in the pathology department. Masaryk Memorial Cancer Institute, ICAM, also quite fruitful collaboration, and also with the biobank institution, BBMRI. Okay, that's all from me. Thank you.
Okay. Thank you very much for the presentation. Again, we have possibility to ask questions. I will ask firstly Slido, nothing. And in the room. Oh, yeah, there is one. Okay. And Marek, you would like to ask? Okay.
So thank you very much for your presentation. I'm here.
Yeah.
And so finally, what is the error rate or success rate when you compare AI detection and human detection of cancer in your institute? Because you are working with somehow standardized data, I would expect, because this is the same lab, the same image formats and so on.
Yes, okay, so we started working with MMCI, so yes, then it was standardized, but now we are also working in multi-centric way. So we try to use data from other hospitals, and it's much more difficult. But okay, it depends on the problem that you are trying to solve. But in the case of the prostate cancer, for example, this is like 0.98 AUC or something like that. So the model is almost always correct, and the pathologists as well. So it's very close to 100% correct. There are problems, other problems in pathology where it's not the case. But still, if you are not over 90%, then it's just academic research. But in most of the problems that we are right in the experimental clinical deployment, then we are very close to 100%. But even if you miss one cancer case, that's obvious to human pathologists, then you are in trouble, right? And this happens to us still. Like sometimes human is able to find it, but the system misses it. What we are working on, and what's maybe the most interesting in this case, is that we also have the explainability systems, like explanations of the models, and we are at least able to diagnose what the model does not see in the samples. Okay, so that's probably the most important part.
Okay, thank you. Here, no, it's the same question.
Yeah.
Okay, so any other questions? Slido? Yep.
The question is, what hardware or software technology or storage is used to store the image data?
Oh, so this is the question not probably for me, because I am from the AI side. So for me, it's like black box. So I'm sorry, but
So infra sees it, right?
Yeah,
that's
infra.
The question. That's the
this is
answer.
infra.
Maybe I will follow up what you mentioned earlier on the paper that you need to do the digitization right, you know. So what I got information from Rudolf Nenutil, that's the pathologist that you are cooperating mostly. So he said that this viewer that you have on the web, that for him it was a tool, you know, because he was like doing this with the screenings. Is it right? This is the kind of right way how to digitalize things that are usually done in offline.
You mean with the viewer?
Yeah.
Yes, the usual process is that the pathologist gets the case, which is a sequence of the scans, and then goes very quickly through it. And in physical case, the pathologist takes the glasses, puts them into the microscope and looks at them. So the workflow in the digital case is have a list of the scans and view them in the viewer. But it has to be integrated. This is something that is quite important, that they don't want to use several softwares on the same patient. That's something that several pathologists told us, or medical doctors, that you definitely have to integrate everything into a single view. Because otherwise there is a chance of error of using different patients in the different softwares. So yes, this is it. This is how it works.
And thank you. And last slide, basically, you mentioned something about selling it, because then the companies are basically, there are no companies over academic research. If I'm not mistaken, you founded one company, and what's the focus of that?
Yes, the focus is to produce the systems that help with the diagnosing cancer, but this is not, of course, not the only one. So there are several companies doing that. So yes, the systems that are able to help with diagnosis in particular cases.
Yeah. Okay, so we have an example of commercialization of these technologies already on the stage. So thank you very much once again. And Tomáš, please sit at the panel. Thank you very much. Okay, next speaker is going to talk about quantum mechanics, advanced data generation for machine learning-driven drug discovery. He is as well from Masaryk University, Saltuk, Eyrilmez. Sorry for that. He as well kind of promised that he will dance on the stage, so he will try, 2 days ago. And he is a postdoctoral researcher at Masaryk University and Sun and University Hospital, Brno, and focuses on computational drug design and quantum approaches to biological system. And last information addressing as well Alzheimer's disease, etc. So welcome him on the stage. This is microphone and present.
So hello everybody, and thank you very much for your kind introduction. Today I would like to talk about our research, especially I'm in the part of the data generation for machine learning studies. So I will try to break down the title into something starting with drug design, especially telling you some information about timeline of drug discovery. So in most of the cases, you might have seen this kind of graphs. What is a drug discovery? What are the phases? How long does it take? And what are the costs, and etc. And basically, you can see lots of information like it's a decades-long efforts with a multi-billion dollars of costs. In our case, as a computational drug design studies, we are actually mostly placed here. So it's prior to the preclinical test, we are searching for huge small molecule libraries, trying to find hit compounds, and then after that, working on hit-to-lead optimizations to provide to the rest of the workflow with high-quality compounds. So speaking about drugs, I would like to create an image in your minds, like imagine this is a protein structure, that's your target, and it's interacting with its, let's say, substrate or ligand via lots of processing. This is extremely simplified animation, but as you can see, that there was something like happening, approaching of the ligand, and after that, some sort of recognition and inducing of the proteins and so on. This is a complicated procedure. So for computational point of view, we are trying to mimic these kind of processes by using techniques called molecular docking, which means that imagine this is the crystal pose of this blue one is the crystal pose in an active site of a protein, and you're trying to predict the structure of the ligand as if it is experimentally tested. But there are lots of things which can affect the accuracy, like, for example, system size. If the binding site is larger, your search space is going to be larger. Small molecule complexity is another problem. For example, if you have a very interesting ligand that you can miss any of those interactions while you are doing your calculations. The binding site complexity is another thing. For example, during this docking process, if you have really hard to solve protein residues around your ligand, it's hard to catch the interactions. Sometimes these can be like flexible, or sometimes the entire protein is flexible, and you need to take account into all of these changes in your workflow. So I would like to just show a sneak peek of our latest results. Just as an example, I would like to show a receiving operating curve for our results versus classical methods. This is the random curve, the dashed one. So in most of the cases, the classical methods can fail where this semi-empirical quantum mechanic or quantum mechanic methods can able to catch lots of valuable interactions. For our tests, we are mostly concentrated on really hard to solve cases. So in our data set here, as an example, has 40 active compounds versus 1,200 decoy molecules, which are meant to make noise and confuse the softwares. And we can say that quantum mechanic methods significantly outperform any other methods. There are lots of curves like that. I will not go too much into detail, but what I can tell here is that, stress out here, that the quantum mechanic methods can come with significantly high performance with a significantly high cost as well, and time. So for that, not to repeat every time, every calculation for on the same target, what we were thinking is that, okay, let's create a pipeline, and then after that, continue with machine learning processes, which we can create some models, successful models. But for that, yeah, we are just actually scratching the surface. So what is it about is the current coverage for drug-like compounds is estimated or enumerated like 10 to the power of 14. But estimated drug-like compounds in general, theoretically, is from 10 to the 33 to 10 to the 60, which means that if this is the Earth, we are actually having a grain of salt. We have to be really fast and accurate at the same time, but for the machine learning applications and trainings, those problems are mentioned in the previous slides also. Like different labs have different kind of results. Sometimes methods are completely different, conditions are different, and these are bringing noise. Reproducibility is another key problem because sometimes you can see some paper, you can go to wet lab and try to reproduce the data and you cannot do it. And another main problem is the bias towards the successful results, because most of the times you can read papers like amazing results, amazing outcomes, outputs, and so on, but no one is talking about the failures. The most important thing, one of the most important thing for the machine learning or AI is also it needs to know what is good, but also what is bad at the same time. For example, that you can see here, one of the crystal structure of a protein ligand complex. And most of the machine learning models are trained by, for example, databases called PDB-bind or something like that, the crystal structures. But if you don't have any interaction, you don't have any pause. So it's like showing the machine learning models or AI perfectly parked cars and try to make it achieve something like a parallel parking without showing the progress. So this is really, this has impacts on AI models. The models are not learning exact physics principles, fundamentals, which are driving these really fragile interactions. And these are really, it's really hard to generalize for novel chemical spaces or novel protein targets. So in our laboratory, we are working on generating multiple binding states for training ML models, which means that now in the first animation, you saw that there's something going on there during the penetration of the ligand. What we are doing is generating lots of states of the ligand inside the protein and inform the model for the process, not only the end state. And we are doing our trainings exclusively on small molecule libraries which don't have any overlap with our test cases. And for that, we are using quantum mechanical calculations to generate labels for training the models on the structures. So this can be only achievable by using high performance computing systems. So for the results, as I showed this rock curve before, and when we apply the training on a small database, a small molecule database, and run training, you can see that this green ML model is almost mimicking the quantum mechanics-based calculations. But again, no overlap with the test set and training set, which means that we are really training model in a good way. It's orders of magnitude faster. It's 300,000 times faster. It was amazing to see that how it achieves just by looking to the structures for a few milliseconds, and after that giving you the structure which should give you the exact results as quantum mechanical calculations give. And yeah, literally successfully learned how to parallel park. So in our laboratory, we are also working with experimental groups. The pipeline that I'm also working on is improved by the inputs and outputs from the experimental team as well. We are focused on Alzheimer's disease research. For example, we are working on ApoE protein, which is a key protein for the late onset Alzheimer's disease development. And for us, it's a very challenging protein because it has no certain cavity. The calculations should be as accurate as possible to capture very weak interactions to be able to get to some sort of drug or understand the function of the protein. So for that, we are working on brain metabolomes, which are the compounds in your brain, to understand the interactions of these compounds with this key protein. And also, at the same time, we are working on small molecule compounds to make some corrections on the activity of the protein. And also, we are collaborating with some other groups on cancer-related drug discovery research, such as breast and melanoma. So the perspectives from our studies is that firstly, creating a library of ML models on key targets. For example, biochemically key targets which are really important for drug design. So that scientists can use these models for their research, for drug design and discovery research. So by using these key targets, we are also aiming for target-specific hit identifications, which means that we can able to find hit compounds, which I showed in the first slide, with a higher quality, which can be streamed to the rest of the pipeline with feeding with high quality initial compounds. So at the same time, these hit compounds can be evaluated by many other models on the fly to be able to get to the really side effectless compounds. So this is another plus is the reducing time and cost, which means that we would need really low computational power to be able to use the same model over and over again for different purposes. So we are also planning to create tools for example, quantum mechanical part to deliver to the people. They can train their own custom models. And eventually, we are aiming for a true generalization. Like this can be seen as a dream, but believe me, 4 years ago, this part was also a dream, so why not? By speaking about providing tools and models, actually in Loschmidt laboratories, this is a common practice for us that we have lots of web servers that people can able to log in and do their research right on the web browsers without needing huge computational facilities. So this work, as I mentioned, we are working with a very interdisciplinary group, wouldn't be possible without my colleagues from Loschmidt laboratories, from experimental team and theoretical teams, as well as from CIRC, CTU in Prague. I would like to thank all of them because the rest of the machine learning models and trainings wouldn't be possible without their magic. And I'm also thankful for the institutions that are supporting our research. And thank you for your attention.
Thank you very much for the presentation again, and possibility for questions. Now asking in the room. Any questions? And Slido?
There is one question. Isn't QM-based docking much slower than classical methods?
It is extremely, like thousands of times much slower and also computationally demanding. But here, as I showed you, most of the docking functions or classical physics-based methods are running on the random curve. So we need something. We need to have really, these quantum mechanic-based methods are really useful for hit-to-lead optimization when you know some sort of scaffold and few modifications and you can go for like few compounds. But it's really hard to get into something like a screening of huge small molecule library. What we are trying to aim is that train the model which can able to at least approach to the quantum mechanic level accuracy, but even faster than the classical methods and docking functions.
Okay, thank you. Any other question? Oh, over there.
Yeah, can I have one question about the future and new type of the hardware as quantum computers? Do you already envisage the usage of the quantum computers in your lab?
We've been in the quantum computing workshop in Ostrava recently. So we are actually scratching the surface. Like at the same time, we are trying to understand if the quantum computing could be used in the data side or data production side or processing side. This is really a new topic and we are still trying to understand. And as the advancement with the quantum computing, I hope we can able to start using practically for generating the data.
Okay, thank you very much. And to connect it what Tomáš was mentioning before, that the AI part of the whole things is very small. You know, you mentioned the drug discovery, and you are working in one of the fields, like the 3 years window, I would say. Yes. How big the use of AI is within this field? You know, how big portion of using AI in the drug development?
I'm mostly concentrated on my part, honestly, but there are lots of usages in other steps as well. For example, in the preclinical stage, clinical stages, and so on, because human metabolome is a huge map. So AI is, of course, giving some benefits to process this huge data.
So I would say that it's similar like the use before in the presentation. Perfect. So once again, thank you for the presentation. And please take the seat. Thank you. And last but not least, I would like to invite Vladimír Ulman from Technical University Ostrava to give the presentation MIFA, Metadata, Incentives, Formats, and Accessibility Guidelines to improve the reuse of AI dataset for bioimaging analysis. And Vladimír is a senior researcher at IT for Innovation, so the Czech Supercomputer Center. at Technical University of Ostrava, and he is a research assistant at Masaryk University as well. And he works with the tools like Fiji, Big Data Viewer, and Mastodon. So Vladimír, welcome on stage, and we welcome you and looking forward for the presentation. Yes, this one.
Good morning, everyone. Thank you very much for the introduction. So I would like to share with you a bit of a story that we have a recent progress in our suffering with annotated data, and in particular about standardizing this. So before we actually do, let's just have here a couple of synchronization slides, so to say. So I said annotated data, so it's data plus some adjectives. So what is this? Technically, it's the in my field I forgot to say, sorry for that. My field is a biological imaging. I'm a computer scientist actually, but I work a lot with biologists. And I'm developing image processing for them. And so the data that I'm often getting is the data that are coming from microscope from the biological field. So they could look a little bit like this on the left. So this would be the data. And what we are seeing here is the annotation to that. And this annotation can come in many forms. It's basically the purpose of annotating data is to explain to a computer what is the expected result, what the user would like to have that would happen to the data. In this very case, we are looking here at the expected segmentation of the nuclei. Nuclei are these blobs on the left. So, and how this can be useful in a computer science at all. So, basically, there are two prevailing use cases. One is for training AI. So you basically, if you think of AI as a black box, that you give it an input image and ask the black box to figure out what to do with it in order so that you get the result, the annotation. That would be the top use case, the one on the upper line. Originally, however, the annotations people were doing it for the purpose of benchmarking, which is the bottom line. Basically, the idea was there that you have an algorithm, it does something to your data, and then so you get a result of the algorithm, and you want to compare with your expected result and basically know what this is. Today, I would say that the prevailing case is the upper one, even though this you basically find in every paper, right? When it comes to quantitative evaluation of your method, then you basically have to do the bottom line. And if you would have no annotation, then obviously this will not work. You will not be able to train anything and so on. And yes, I already said that AI basically was the when AI came around, people started to think about annotations more seriously. And since we are now in Brno, I would like to actually mention that Brno has a history on doing annotations. Some of you might have heard that there is a cell tracking challenge being executed over here in Brno at Masaryk University, and this is a resource that originally actually came for this very purpose. We wanted to see how algorithms are doing well, but nowadays most of the people use it as a resource for the training. So the situation is that, okay, we have some annotated data out there. We have also a lot of AI models out there that can do stuff. They actually work pretty well. The issue a little bit here is that the AI today, most of it is that it excels on a particular image processing task, on a particular data, and that's where it ends. So if you move to another lab in a very same biological room or biological building, for instance, they produce a little bit different data, and then the AI, the original method, is just gone. It doesn't work well, so you have to come up with another one. That basically means that if you want to cover the whole biological field, then you have to come up with many models. That's one option of doing it. It's a little bit unfortunate for the user, because that means that the user has to be switching the models, right? The user acquires a certain data, and then he has to kind of decide which model to use. Eventually, he can try all the models and then choose somehow the results, so it's a little bit difficult. I would say what we want to do is that we want to come to a AI method that basically has seen it all, has understood it all, and can do all it. It's a little bit similar to our human brain. We also don't switch brain when you drive car or when you brush teeth, right? You do it still with the same device. So we want to do the same thing. And in order to do that, the strategy that is somehow generally accepted is that you basically create a big AI and you give it a lot of training data, a very variable training data, and you hope that it somehow absorbs it into you. So in both cases, we are, the claim was supposed to be here that we are a little bit in a lack of such data, that we would like to create more annotated data and share them, of course, with us. And the MIFA, we're finally getting to the point of the talk. The MIFA is basically a set of recommendations that we put together to make sure that people don't share the data in various ways. So indeed, some time ago, a group of people were invited. Yeah, I was also part of that group. That's why I'm telling you today. We were sitting together for a couple of days and thinking, and then trying to put together all, like, from all the aspects, what would be ideal if we want to share our data, our annotations, actually. And this materialized in a paper, so there is a sort of a permanent storage of what we have come up with, and that will soon appear, will be published, so you can all read about that. This story is basically about the annotated data, but I wanted to bring to your attention that next to the MIFA, there is something that's called a REMBI paper, which is recommendations for metadata for biomedical images. So if you recall at the beginning, I said annotated data is the data plus the annotation. So now this story is that the REMBI is basically a description of metadata for the data. And the edit part, the annotation, for that we also needed to have some sort of metadata so that we can eventually find it and even understand. If you share the annotated data set somewhere, it would be good to know what was annotated there, how much the people were trying how well they were trying to annotate stuff, or what was the annotation, because it can come in many ways. And we believe that this paper could actually have some effect because it's connected with the REMBI paper that everybody knows in the field, because there were some stakeholders who are, like big consortia across Europe, and also the basically two prevailing repositories of the data in Europe or in the worldwide. One of them is Bioimage Archive, and the Bioimage Archive, this is actually a few days old situation. They recently put it on their website, so now it's sort of officially acknowledged that next to the REMBI you could have MIFA, and I would like to tell you what this is about. Yes, okay, and one thing I also wanted to take this opportunity when there are funders around. I wanted to tell you that to create a good annotated data is really an effort. It takes time, and we know that time is money. So while I totally cannot say that every day there are like lots of annotated data sets coming out, but there are tens of papers coming out every day. So we would like to kind of tell that in the field there should be maybe people who would be actually like professionalizing themselves in doing the annotations. Ideally, annotations should be done by experts, but as you heard from Tomáš, this will probably never happen. They just don't have time for this, but they want the results. Okay, so here was just an overview. On the left-hand side, you can see there are different ways of annotations. I was showing you annotations for segmentation, but you can have a classification, you can do bounding boxes, you can have labels, and so on. And then on the right-hand side is how we were thinking about how this could be described, and it basically comes down into four sort of main themes. One of them is the metadata itself. So basically, we have noticed that in the datasets that are up there, one of the things that is missing is the sort of a context, a biological context. So you look at the data and you don't understand why people were creating it. Eventually, you know that it was because they wanted to train the AI, but still, why the biologists wanted AI to do something on that images, and what was supposed to be the expected result, and why was this created. Then there is a lack of science. And we were also thinking that we are missing a little bit in the field some connection to created models. So we have on one hand repositories like Hugging Face, where you have a models. There is maybe somewhere I mentioned that they were trained on X and Y, and then somewhere else you can download the data sets. But the connection there is a little bit missing. So this is one of the things that we should maybe be thinking about when we are building up a future repositories. Now for the image data itself, you already heard from me that we are thinking that the best idea would be to use the REMBI model in a biological imaging pilot repository in EOSC. This is actually the way that we are walking. For the annotation, for the metadata about the annotation themselves, let me highlight here a couple of things. One of these things that we were thinking that would be good to to echo, to be part of the annotation would be something as a confidence level of the annotator himself or herself. That would tell us basically how much the person would basically, ideally, honestly, say how hard he or she were trying. Then we were thinking something like a coverage, because there are data sets out there that doesn't annotate all the objects in the image and only parts. So this would be also good to know before you actually start downloading anything, and so on. Yeah. Then I already mentioned that we think that people should be encouraged to do that. We were thinking or discussing how people could be kind of motivated to put stuff on the internet and then do the annotations. We were thinking something like an impact factor, so that people would, because a lot of scientists are a little bit egoistic, so they are happy if they see their name somewhere on a like often downloaded data set, so on. And supporting development of tools for annotations and events where people get together and actually try to annotate and advance stuff. Then we shouted out a couple of names when it comes to formats, like so that people don't come up with their own ideas and rather try to stay with something that's kind of known. One of the rising stars that I would like to bring up is for the biology field. There would be the format OMISAR, which is something that we call cloud ready. It's just not a buzzword. Cloud ready in our realization basically means that you don't save the image as the whole thing, but you actually take these little tiles or boxes and you save them one after another. Each is a separate file, and that can give you this sort of a Google Map effect. So if you are looking on a Google Map, you basically download only the tiles that are relevant for what you are currently looking at, for what you have on the screen, and you don't, if you want to look at the map of Brno, you do not download the full map of the whole Republic. Right, and with it comes some more advantages. One of them is that you can, of course, take these individual tiles and process them in parallel. People can be, annotating or collaborating, annotating different parts and uploading onto the same storage, and so on. And it also is it's a little bit of paradigm change for the software, for the applications that are working with these images, because before that we were always had in mind this expectation that an image is a big block of a memory that of course fits into your computer memory. But if you do it this way, then this is no longer true. Your software has to realize that maybe it's working with something that's actually very large and you have only a portion of that, and there could be places in the image that you simply don't have in the memory, and the software has to deal with that. That unfortunately means that we have to do a lot of changes on the application side. Yeah, for the sake of time, I would now hurry up a little bit. For the accessibility, I already mentioned, we have to think of our repositories where we will be using the annotation for the metadata and putting data and models together, so that we can advance the field, the AI. This also, when I was talking about the metadata of the annotations, we have totally no idea what sort of ontologies we should use. So this is an open question. We of course understand that ontologies are a good thing and we should be trying to use them, but we are not aware of any that would, for instance, describe your self-confidence when it comes to annotation, or what was the coverage, right? So we have to think about that, and I already said that we have to do ready-made tools. Right, okay, so this is the last slide. This is a conclusion. Basically what I wanted to say, the message here is that let's forget about the paper actually. That means that we are on a certain way, on a certain direction towards standardizing, and I think a lot of people here in the room were thinking to themselves like, hey, I'm maybe doing something similar in the EOSC. So we see and realize that there is a big overlap. I think we can sort of jump on this, and EOSC I think has a very good chance to basically give us the missing pieces that we've set up the directions for the biomedical images, and through the EOSC activities we can actually finish this up and advance it. So it's good that we have this, and with that I wanted to thank you for your attention.
Thank you very much for the presentation, and now 1-2 questions before starting the moderating discussion. Anyone in the room? Oh, Saltuk, let's go. You can ask the question. If you can pass, please, the microphone. Thank you.
So my question is that I don't know how frequent it is, but if someone comes with an entirely new kind of annotation and tells that this is a new kind of property, new annotation is needed. So is it happening like this people or group is putting the rule for that one, or would there be some sort of like discussion, like how to decide, how to integrate, and so on?
Thank you for that question. I would say it really depends on the group. We have in our field online forums and chat and these kind of things. Some groups are such that they first start discussion on there and then just let it run for 1 or 2 months and then hope what people will, conclude, and then they do it. And there are groups that just do it. And then they are basically trendsetters, right? They started somehow, and then the other people, some of them follow if they like it. Sometimes you have people saying like, okay, I know there's this format, but maybe we can do better. And then there comes another format, and then it gets wild. And that's what we are trying to avoid, ideally.
Okay, thank you very much. Any Slido question? Anything? Nothing else? So I have one last question before joining the panel. What's Coco JSON? It really drew my attention. Can you describe the format? Thank you.
Yes, of course. So Coco means Common Objects in Context. It is a data set developed by Microsoft. It's basically not meant for biological data because it's common objects. So you have cars, apples, fruits, and these kind of things. But what we like about this data set, it's not really the data itself, but it's how they are describing what is displayed there. And this is in the JSON file. And they are basically describing it with a mask. So there you have a perfect outline of the objects that are there. Then next to the mask, there is a bounding box, which is the region, and there is also a class. So this is one of the few data sets where you have actually 3 types of annotation to the same data.
Okay, thank you very much. So once again, thank you very much. Please, and please take the seat as well, and take the microphone with you, please. Thank you. Okay, I will pass another microphone here, and I would like to ask Mr. Petrík as well to join us at the panel. So basically, the concept of the panel is to have a discussion between representative of Czech use of AI within the fair data, etc. So for that reason, Mr. Koskela is not in the panel. Actually, he had to leave himself, so that makes sense that he's not here anymore. But that means that we were designing, because this is the EOSC Czech National Tripartite event, so we were designing it as a Czech panel and Czech use cases. Okay, so I will just go and sit next to you, and we will start with a very simple question. All of you tackled it during the presentation, and that's the role of data in your AI-powered research. So if I can ask Jan to start with the short or wide answer, as you want, and in the meantime, you can start thinking about any questions that you would like to ask to all the panelists. So please, Jan, short or long answer?
I think short, because you always keep on time, so we need to be short. But never mind, the data is the basement, of course. So in our institute and in our research departments, we are keen on data. But I think one presentation was mentioned that not the only success data are important. So we are also try to make the change in our researchers in order to save, annotate, and properly use also unsuccessful data sets or unsuccessful experiments. So that's something we need to build up the repository in order to be used afterwards. So that's something we want to increase the availability or usability of the data, instead of just presenting the data which are in the article, which is successful always. So we need to save also the data which are unsuccessful or experiments not unsuccessful.
So basically the negative data are as well important as the positive one.
Yes, of course.
Perfect. Thank you very much. The same question goes for Tomáš, the role of data in your AI-powered research.
Okay, so I think that I've said most most of that in my presentation, but we of course are dependent on the data from medical institutions. So there are also some legal problems with these data, sometimes big problems, administrative problems. But anyway, okay, we are dependent on the data that we use to train the models, and also, as I tried to stress, on the collaboration, so understanding of the data. That I think is the most important thing. That we are working in such distant areas that we don't understand medical experts, and medical experts typically do not understand us. So this is maybe the most important thing, not just the data. The data set is that. What is most important is the communication of the experts on the data. That's something I want to stress. Okay, thank you very much. Saltuk, please. Same question.
I think for me the most important take-home message is that, as also you mentioned, I showed in the presentations also that the AI models should be also trained with wide variety of data, especially for these unsuccessful cases that we can able to generate. So we are actually synthetically generating these unsuccessful cases and showing the machine learning process that this is bad, this is bad, this is bad. You only have just one or few chances to be successful, but we are also trying to show thousands of unsuccessful cases to be able to get to some right answer.
Okay, so if I understand it well, so negative data, synthetic data, another important element in that.
Yes,
yeah?
yes.
Thank you very much. Same question to Vladimír.
Yeah, so I agree with all what was said. That pretty much holds for our field as well. Data is absolutely crucial. I mean, otherwise I would have nothing to process. We have a little bit of an issue that in the biological field, there's like a lot of variety of what is the content. It's not like if you do computer vision, the cars look more or less the same everywhere, but the cells are really different, and there's like a key non-stop evolvement and development of microscopy techniques that gives you also a little bit different data. So when it comes to sharing, before that comes the creation of data, and this is where we struggle also a lot, because as I said, experts don't want to do that. There is a difficult communication with them to understand so what they are after, so that we could maybe do it ourselves. And unless you are trained, it's also very difficult for us to create annotations and maintain the quality, and then all the data is super faint. And we have issues like, it depends if you are doing annotations in the morning or in the afternoon, where the light is on your screen and so on. So it's crucial, it influences us, and it's unfortunately not only the sharing issue and annotation, there's like much more that we have to fight with.
Yeah, so variety and complexity basically of the data.
Yes, yes, absolutely. Yes.
Okay, thank you. And passing to another Vladimír on the panel.
Yes, so yeah, in robotics, a lot of the data is now important as well, but it's not only things. So data are important for generalization and that aspects of robotics, but there is also safety which needs to be achieved. So there is also safety layer, which is not data dependent, and should maintain that as well.
Okay, thank you very much. So to conclude this question, so from negative data to important, that people are important element of that, to synthetic data, variety and complexity, and to safety, and to look probably to ethical issues as well on this kind of stuff. So thank you very much for answering that. I would ask, do you have any question for the panelists as well, or from Slido? If not,
yes, there's one question.
Thank you.
So how important are persistent identifiers for AI? Do AI models use bits to find relevant data by themselves?
So persistent identifiers, probably, Vladimír, to you, because you were talking about the standards, etc.
Yes, yes. So persistent identifiers, of course, are difficult, but I would say mostly for what they were designed to, so that you can, you have identifier of a data set, but the AI itself, the network, as far as I know, they're not using it, and it could be. This is actually happening. A part of the question is the answer is that if you download an implementation of a certain network and you want to retrain it, there are in the API usually the cases that you say I want to retrain on my data. I give it my folder, And I also want to include dataset A and B and C, right? That you can say, and the software will really download the dataset from that. But it's not that you give there a persistent identifier and it would use the means that we are, trying to do in EOSC that would basically route you to the data and fetch. That's not the way, unfortunately, yet. It's really hard-coded path to somewhere. That's what's happening.
Okay, thank you. Any other comments about persistent identifiers? No, so we will move to another question that we prepared for the panel. So the preparation of quality data for AI use is one of the key aspects of success. We talk about it. Can you describe how you are handling preparation of data for AI use within your field of expertise? Basically, especially how you are handling the topic of labeling data, etc. Basically, how to do this quality, fair data. And maybe if Vladimír can start. Thank you.
Yes. So we are collecting data by teleoperation. That's costly, but then we have it annotated. We are also using the simulations, that it is easy. And if you have external data, we are relying on other AI techniques. So we can do segmentations now automatically with foundation models. So we're trying to use that as well.
And if you can comment, it's more automatization than I would say manual work, or vice versa today.
So I would say it's a combination. So we have these foundation models, they can give us something, we can use other modalities to verify that, but then there is still some verification by humans. And if you want to have really quality data, then we need to do it manually.
Okay, so thank you very much. And Vladimír, number 2, in this direction, please.
Okay, yeah.
Thank you.
So our answer to having better quality in terms of annotation is that we are trying to build tools to help people to do the annotations, because the issue with the annotation is that this is a annoying task, those of you who have tried, and it takes time, and people are not machines, so people get tired, and that means that they start to simplify their jobs. So at the beginning, typically you try to annotate and you are very punctual and you go to every corner. And then as the time progresses, you kind of make your life a little bit easier. That this is what we see on the annotations. So we are trying to create tools that would make people's life easier. It's a little bit of fake in a way because we are using AI, so it's like an AI for AI. But the trick is that we don't allow the software to do the segmentation, the annotation for the full image, because then people will be overwhelmed and they will not try to visit every single cell and do the fixes and changes. The software is intentionally interactive, and it really allows you to go on a little region, little step by step, so you never get kind of like flooded with results. And then we hope that there is a chance that people could fix quickly, because everything is local and just small. And the machine the software that's kind of doing the pre-drawings or pre-annotations, pre-labeling for us is another AI. And this time it's foundational model actually. But there needs to be a human in the loop at the end of the day, otherwise it would not be annotation.
Yes, so moving to as much automatization as possible, but still the humans are important.
Yes.
Thank you. Saltuk?
For my case, I'm mostly in the place for generating high quality data. So it's finding the target proteins and finding their active compounds and make some confusion for that, and generating a set which is like firstly testing and validating the method, validating the preparation steps and everything, and then labeling the data for further training. Yeah, most of the parts of the pipelines are already automatized, but overall a human interaction should be there. Unfortunately, there is no AI for AI, but someone is really have to sit there and smash the keyword. But after that, this high quality data is really useful for machine learning and AI training.
Okay, thank you. Tomáš mentioned that already the humans are very important for that in that field, but maybe in the lifetime of your biomed AI project, do you see any more automatization, less automatization, any progress?
It's not about automatization, but more about using weaker annotations. So we basically started with images annotated by hand, not completely pixel level, but like annotations of the tumors in the scans. But we also tried other techniques where we simply had just information about presence of or absence of cancer in the image somewhere. And our results show that, also results of other groups, that if you use more images, it works. So I can compare like 1,000 slides with detailed annotations give us very similar results to 10,000 slides with just information about presence of or absence of tumor. So we are saving time of medical experts just by asking as little as possible. And quite often, very surprisingly, it works.
Okay.
So that's the approach.
Thank you for the point of view. And Jan?
So because we want to achieve more reproducibility and more explainability of our data, so for us it's about the processes. So we want to standardize the process in order to be well documented and know how the labeling or annotation should look like. And in order to help people to work with it, we also help them or provide them with the tools. So as much possible to use it, I don't know, automate, but it's not, of course, just humanless, but we want to help them to do the tough work easily. So that's our approach.
Thank you very much. So basically humans are still needed. AI is not taking over, I would say, in this field of annotation, at least, and working with labeling and preparation of fair data. Any questions from the audience? Or Slido? Nothing. So I would have last question for you, and you can have a quick answer. But to connect the topic of AI to the research infrastructure that we were discussing yesterday, how the research infrastructure is helping in your field with AI? What's the support that you are getting, or collaboration on anything? So Jan, please.
So for our is crucial. So that's essential, because otherwise we won't work. So we are using the EOSC infrastructure for storing data, for calculation power. We also involved in a project of having the metadata or repository with the proper metadata. So it's Dantec. So it's crucial, because we want to make it as much usable and as much standardized, and we want to reuse what already existing, because otherwise we invest useless.
Okay, thank you. Tomáš?
So in our case, we also need the infrastructure, and as I said in my presentation, there is a team that is working in coordination with us, and we store data there. We use the compute infrastructure. So yes, it's crucial, and I'm quite happy that I don't have to know the details of how it works, because it's operated by competent people, and they are very, very closely working with us. So that's great.
Okay, thank you very much. Saltuk?
For us, again, it's essential. Without the HPC infrastructures, we cannot do anything at all. So we use Metacentrum, we use IT for Innovation supercomputer, we use Lumi computers to be able to generate high quality data. Sometimes all of them at once, sometimes partially for some purposes. But without HPC, we cannot even move forward.
Okay, thank you. Vladimír?
Yeah, so I'm coming from IT for Innovation, so I think
so you are using, right? Yeah.
Yes, yes. No, but I want to also. You totally cannot train your network on a laptop, right? You need big machines, and we have there a lot of compute power and a big storage and everything. So there's basically no limit for us. So we're totally depending on that, and we're happy for that.
Thank you. Another Vladimír?
Yeah, for us it's the same. Without IT for Innovation, Lumi would not be able to achieve the results we have. So it's very crucial.
Yeah. Okay, so basically to conclude the panel, infrastructures are key for AI. Infrastructures are key for fair data. On the other hand, AI is key use case, for infrastructures, and key use case for fair data. So with that, I would like to thank once again to all the panelists and to you to listen to that. And please stay on the stage. That from the organizational point of view, I will tell a little comments about the lunch, etc., and we will close this morning session. So Just give me a second. Okay, so basically, I'm now the person between you and your lunch, so this is not good. But the conference is not ending by the lunch again. Please come back to this room for the open session on fair data. And I have an annotation here, just give me a second. This will be very interactive. So very important FAIR topics and the general requirements for FAIR. You will hear, for example, a presentation about research data verification and core facility MAFIL at SATEC of Maastricht University, how to make research software FAIR, and a very practical and hands-on experience. So this is what's going to happen here at the room. And the others who got the invitation for the closed meeting regarding the pilot repositories, Dan, can you stand up, please, just that we see you? And this is the guy that is going to lead the workshop on the pilot repository. So you will meet after the lunch at the room number 4. It's that direction. Okay, so yeah, and who has no invitation for that meeting, so please come back after the lunch and we will talk about FAIR aspects and together in collaboration with the concept of EDUC Alliance as was mentioned. So I would like to, another organizational thing is please sign yourself at the registration. This is important. We need this signature and to prove that you are here at the conference. That's another thing. After the afternoon program, go to the tower, don't forget. And now, because my colleagues don't know it, but I would like to ask everyone from training center and secretariat that they were working on this conference to just stand up, and I would like, if we can basically clap the hands for them, because it was a very nice conference, I hope. So thank you very much to all the organizers locally. And if you can stand up, please, and we have agreed with the photographer that we will have a photo of you as well.